Professor. So, as you know, I am in Mexico right now, and this experiment actually was quite easy for me since I had a large amount of sand everywhere I go. And so I used some of the sand that I found here. I also did some research and got some different ingredients to do this experiment with that were the ones that are usually found in a store-bought kinetic sand. So basically, to get started, the ingredients that are in kinetic sand that I used is sand, obviously, and dimethicone, which is a silicon. I think the actual compound is called polydimethylsiloxane, or PDMS for short. And so basically, in this kinetic sand that I made, it's basically the formula is SiO2. So it's a silicon atom with an O2 molecule. And basically, so how the kinetic sand works is what it looks like. The atom, what it looks like is it is a long snake with or what the molecule compound looks like is this long snake with silicon oxygen, silicon non-organic belly, and then a organic non-polar scaly surface made up of methyl groups. And silicon atoms are larger than the carbon and hydrogen atoms nearby, and so they are actually larger or big enough to draw electron density away from the hydrogens, which creates a slight polarity, and it provides the possibility of hydrogen bonding. So also I'm reading from my notes that I took from doing some research, watching some more videos, reading some extra stuff. So basically, now that there is a possibility of hydrogen bonding, you combine this with the fact that in the silicon oxygen belly, each oxygen also has a lone electron pair, which means there's a slightly negative electron density sitting out there just like waiting for some interaction. And so if you consider also that the PDMS polymer is very flexible, so the molecules are able to move around so that it is the most ideal so the molecules are able to move around so that the most ideal interactions occur. This means that the PDMS chains get close enough to where they shift their parts around in ways that allow for possible multiple hydrogen bonds. And so for hydrogen bonds, they're intermolecular interactions that are not actually chemical bonds. They're, as we know and as we've learned in this class, they are an interaction that causes molecules to stick together. In normal hydrogen bonds, they're usually much weaker than chemical bonds and can easily be broken. Also, the sand-silicon dioxide bonds are extremely flexible, and there all of the oxygens with their electrons also are just wanting to join the interaction. And unlike the carbon-hydrogen tetrahedra that are locked into their angles pretty rigidly, the silicon-oxygen tetrahedron angles that are formed in this matrix of silicon dioxide, these tetrahedron angles can also be of varying angles, varying measures, and so they're very flexible. They orient themselves in a way that allows for the formation of more hydrogen bonds. And then because the sand particles are so small, we can imagine that these interactions are very weak, but the closer you bring the material and compact it harder, like in the sand, it will because the hydrogen bonds are able to form then as it's pulled apart. I wrote that wrong, hold on. Yeah, so then as it's pulled apart, the weight of the sand particles overcomes the attraction of the hydrogen bonds, and the molecules are able to separate easily. That's why the kinetic sand almost looks like it acts as a liquid, but also can act as a solid. And so, let's see. yeah, so that's pretty much it. That is how kinetic sand works. Here is my little kinetic sand ball that I got and made in the kitchen here at the hotel I'm staying at, and I got my sand from out here. And I used the PDMS instead of like the soap and cornstarch and everything, just because I wanted it to be more like the store-bought kind that has that SiO2 orientation. So I think that's all. That is my presentation on kinetic sand. Thank you.